So at the top of the second page of notes in 3.4, a lot of words here, a lot of reading. Let me see if I can summarize those in kind of a quick version that kind of would make sense what they're talking about here. All right, fundamental theorem of algebra, which sounds really important, right? If it's the fundamental theorem of all of algebra, that sounds like a big deal. Says that if f of x is a polynomial function where the degree is greater than or equal to 1, and you can have complex coefficients, that just means you can have any number you want, including imaginary, out in front of an x squared or x to the third, then there's at least one complex zero. Now, what a lot of people do is take that one step further, and they say, oh, well, if you have an x to the fourth, maybe it's 5x to the fourth plus blah, 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 whatever's after it. If that exponent's a 4, that means there's going to be 4 zeros. If you had, 7x to the third plus whatever, then you're going to have 3 zeros. If you had an x to the fifth, then you're going to have 5 zeros. So whatever that exponent is, that's how many zeros you're going to have, okay? Some of them could be imaginary numbers, okay? They could be complex, but that's kind of what that fundamental theorem is saying. Linear factorization theorem. We've talked about this, but now we're officially giving it a name. Let's say that -3 is a 0, or it's an x-intercept where the graph hits the x-axis, then that means x plus 3 is a factor. If +5 is a 0, or the graph hits the x-axis at +5, then that means x minus 5 is going to be a factor. So that's just saying, hey, you could connect together your zeros with factors, okay? Conjugate zeros theorem, we've talked about that. So that's just saying that if 3i is a 0, then so is -3i. If 4 minus 2i is a 0, then 4 plus 2i is a 0. They're just saying that imaginary zeros come in pairs, okay? And then the number of zeros a polynomial has, just like we were saying, whatever that exponent is, that's how many zeros there are, okay? Now, you will have to count for your multiplicities. So, in other words, if x minus 3 squared, I had 2 sets of x minus 3, then +3 is my 0, but it would have a multiplicity of 2. It counts twice. So the graph would touch and then go back the way it came, okay? So we can kind of put all 4 of these things together into some problems here, okay? All right, so here's what's going to happen next. And one other thing about that. Let's say that we have an x to the fourth. When I graph something that has an x to the fourth, I think we mentioned this maybe 3.1, we expect there to be kind of 4 sections to my drawing. 1, down is 2, up is 3, and down is 4. So I've got kind of my 4 sections here. 4 segments, up, down, there's 4 sections. What your book is going to do when you're working through some of your homework questions, they're going to ask you how many turning points there are. Turning point is how many places it changes directions. There's one, because it was going up and it turned and went down. Here's a second one, because the graph was going down and it turned and went up. There's a third one. It was going up, it turned and went down. So we would say that this graph has 3 turning points. And if you'll notice, if there's 3 turning points, the actual degree is 1 higher. The exponent was 4. Okay? Now, occasionally, you may see an x to the fourth that only had 1 turning point. And the reason for that is, there's my 1 turning point. If I increased it by 1, I would predict it to be an x squared. This looks like a parabola. But imaginary zeros can mess things up. So if imaginaries come in pairs, there's 1 turning point. We expect the exponent to be 2, but if there had been imaginaries, those would have been in pairs, and that's why the exponent could be 4. And they generally don't try to trick you by asking you, hey, what do you think the degree is? And you go, oh, 2. And they say, no, wrong, it was 4. They generally don't try to trick you. They let you just count the turning points and know that 1 higher than that is probably what your exponent was. But realize it could be, add 1 and then go up in multiples of 2 because of imaginary zeros. That does happen. Okay, so here's what they're about to do. They're about to give us an equation, and they're going to say, hey, find all the zeros and the multiplicities. Sometimes they'll even say, write it in factored form. Well, where do we start at? Okay, so what you could do is go back over here, pretend that we're back, 30, 40 years ago, and we don't have a graphing calculator. what we could do is list our possible rational zeros. And once we have our list of possibilities, we could do synthetic division on those different numbers until we find one that works. Okay? So for instance, I could say, oh, well, what are the factors of 3? What are the factors of 2? And I'm going to do synthetic division until I find something that works. Okay? However, because it is, 2020, we can actually graph this in our calculator. Okay? So that's what they're suggesting we do first. They're saying, hey, you got a graphing calculator, use your technology, graph it, and look for x-intercepts. If the graph appears to touch at a certain number, good chance that that's a 0. So do synthetic division in step 2 and confirm that it's a 0. Remember, if it's a 0, then the remainder will be 0 in your synthetic division. You've also got a depressed polynomial at that point, so you can keep dividing those depressed polynomials until you get to just an x squared, until you have a quadratic. Once you have quadratic, you could do quadratic formula or factoring to get those last 2 zeros. Okay? All right, so that's a lot of words to say that. Let's see what that looks like in application. Okay, so here's a function right here. Notice there's a degree of 4. So I'm going to have 4 zeros. Okay? I should have 4 little zeros, 4 little factored pieces once I get it in factored form. I could list my list of possibles. Probably be, let's see, the 3 numbers divided by 2, so it could be plus minus 1, plus minus 3, plus minus 1/2, plus minus 3/2. That's my list of possibles. And I could do synthetic division until I find one of those that works. But we don't have to live like that. It's 2020. So I am going to just graph this in my calculator. 2x to the 4th plus x to the 3rd minus 5x squared minus x plus 3. And when I graph this in my calculator, it appears, if it'll ever finish graphing, it appears that it hits the x-axis at positive 1, at negative 1, and then I don't know what this other number is. Of course, I actually do. I bet it's negative 3/2 because that would have been on my list. But if I didn't know that, okay, if I'm not really sure, I could go from there. All right, so I'm going to make a note that calculator seems to show negative 1 and positive 1 are zeros. Looks like it touches at negative 1, looks like it touches at positive 1. Okay, so I'm guessing those are zeros. Furthermore, over here at positive 1, the graph came down and touched at 1, and then it went back up. It bounced there, okay? So if that's really the case, if it touched there instead of crossing, it could be a multiplicity of 2. Could be an even multiplicity. All right, so I'm going to take that 1 that I'm pretty sure is a 0, and I'm going to do synthetic division on this polynomial. I'm going to write all my coefficients. 2, 1, negative 5, negative 1, and 3. And if 1 really is a 0, like it looks to be in this calculator, then my remainder should be 0. Let's see if that's what happens. 1 times 2 is 2. Combine, multiply, combine, multiply, combine, multiply, combine, and sure enough, we got a remainder of 0. Okay? Now, these are my coefficients in my depressed polynomial. I had an x to the 4th, so if I wrote this out, I'd have 2x to the 3rd plus 3x squared and so on. But rather than write that whole thing out, I'm going to continue my synthetic division with the next number. Now, I was pretty sure that this graph touches at 1 and then goes back the way it came. So that means it could be a double root. It could be a multiplicity of 2. So I'm going to try 1 again. Now, if it was crossing, like over here at negative 1, it's just crossing. It's not touching and going back the way it came. It actually crossed all the way through. I would not try negative 1 again. Okay, but I'm going to see if this works. 1 times 2 is 2. Combine. 1 times 5 is 5. Combine. 1 times 3 is 3. Sure enough, when I combine them, I get 0. That means 1 was not only a 0 once, but it was twice. It had a multiplicity of 2, which I suspected. Okay, the other number it looks like it touches is negative 1. So I'm going to try negative 1 in the box. By the way, it does not matter what order you try these with in synthetic division. They'll work in any order you get. So bring down my 2 times negative 1 is negative 2. Combine to get 3 times the box is negative 3, and my remainder is 0. So look at that. I found that 1 is a root. It's a root twice. It's a double 0. Negative 1, and then I've still got this depressed polynomial. Now, if you look, it looked like it crossed maybe around negative 1.5. Kind of hard to tell where that number is. So I can think about this as my depressed polynomial. So I had a 2x to the 4th. This division made it a 2x to the 3rd. The next division made it 2x squared. The next division makes it just a 2x. So I've got a 2x plus 3 as this depressed polynomial. If I set that equal to 0, I can finish solving. I can minus 3 on both sides. 2x is negative 3. Divide by 2. X is negative 3 halves. Negative 3 halves is that last 0. That's negative 1.5. And sure enough, I bet you negative 1.5 is that last 0 right there. Okay? All right, so I was expecting 4 zeros. Those zeros are 1. Notice that had a multiplicity of 2. Negative 1. The negative 1 just worked one time. It had a multiplicity of 1. And then my last one is negative 3 halves, and it had a multiplicity of 1. When I add those up, now I have to account for my multiplicities. This one got used twice. So 2 of these, 1 of these, 1 of these, that adds up to 4. And sure enough, my degree was 4. Okay, so that does work. So notice what we did. I used my graph to kind of help me predict what the zeros might be. I did synthetic division to confirm that the remainder was 0 and they worked until I got all of my zeros. Okay, let's try another one here. Find all the zeros of this graph and their multiplicities. Now, we could list our possibilities. Okay, factors of 5 would be 1 and 5. So plus minus 1, plus minus 5. Only thing it can divide by here is 1. So I'm going to have plus minus 1 and plus minus 5. So I know that it's not going to hit the x-axis at 2. It's not going to hit the x-axis at 3. Okay, you don't have to do this, but you could. So when I graph this guy, x to the 3rd minus 2x squared minus 14x minus 5. When I graph it, it appears that this one is hitting at positive 5. Now, I'm not sure about these over here. You know, is this negative half? Is it negative 2.7? Not really sure. And notice 1/2 is not in my list of possibles. 2.7 is not in the list of possibles. So I'm guessing that these could be irrational numbers where they're touching. Okay, could be some kind of square root symbol that we don't know. It's not 1/2 or anything pretty like that. So I'm just going to test the 5. That's the only one I can really test that I'm pretty sure I know what it is. So I'm going to say appears to cross the x-axis at 5. I'm pretty sure 5 is one of my zeros. Let's try it. If 5 really is a 0, then when we do synthetic division with 5, our remainder should be 0. Okay, so let's write out our coefficients. 1, negative 2, negative 14, negative 5. And sure enough, it worked. By the way, if you're struggling with the synthetic division, go back and you can keep practicing that in the 3.2 or 3.3 maybe video. I think 3.3 might have been where that was at. Okay? All right, so now we are left with a depressed polynomial. I don't know any other numbers to try. On the previous example, it was clear. It was crossing several places. I knew several numbers to try. I don't think it's real obvious here. I can't tell if this is negative 1/2. I don't think it is negative half because negative half wasn't in my list of possibilities. So I don't know what this is. So I'm going to take my x squared plus 3x plus 1. That's my depressed polynomial. I'm going to set it equal to 0, and this is a quadratic. If I can't factor it, I could use quadratic formula to help me find those last 2 zeros. How do I know there's going to be 2? Because my exponent was 3, so I needed 3 total zeros. I found 1. Now I need the last 2. So my a is 1, My b is 3, my c is 1, and I can use that quadratic formula. I can use that quadratic formula that we've been working on. All right, so x equals negative b. b is 3, so negative b is negative 3, plus or minus the square root of b squared, so 3 squared, minus 4 times 1 times 1. A and c were both 1s, all over 2a, and a was 1. Okay, I'm going to work this out. So I need to do 3 squared minus 4 times 1 times 1. The number under that radical should be 5. So negative 3 plus or minus the square root of 5 divided by 2. Okay. Notice 5 doesn't have anything that will come out. It's not like it's a square root of 9 and something can come out of the radical. That's the best I can do. 3 won't get divided by 2. Square root of 5 won't get divided by 2. Okay? So my zeros, I have 3 of them because that was my exponent here. My zeros are 5, okay, with a multiplicity of 1. Negative 3 plus square root of 5 divided by 2, and negative 3 minus square root of 5 divided by 2. And each of those has a multiplicity of 1. So all 3 of my zeros here, the 5, the negative 3 plus root 5 over 2, and negative 3 minus root 5 over 2, all of those had a multiplicity of 1. Okay, so when I add up my multiplicities, I get 3, which is what this coefficient was. Now, just so you know, if I type negative 3 plus square root of 5, and I divide that by 2, I get negative 0.39, let's say, negative 0.38. If I do negative 3 minus square root of 5 and divide by 2, I get negative 2.6. Now, why am I bringing this up? Because when I look at this graph, this 0 right here, sure enough, is around negative 3.8. This 0 right here, sure enough, is around negative 2.6. We couldn't tell by looking that those were the decimals, but once we have them in that radical form, we can verify and go, oh yeah, that's about what they were. Okay? All right, so I think that's good for this video. We'll try some more examples in the video part 3.